sorry, the video ended there. In the case that there was a lot of training data where these are all circles, a little cluster of circles, we would be more confident that this one shouldn't actually be a star. It should actually be a circle because we have a lot of evidence of many circles in that area. So with so few data points, it's kind of hard to tell. So let's now introduce the really important idea, which is a decision boundary. So a decision boundary shows the border between different regions of space where your classifier will make different predictions. And here the decision boundary looks like kind of a wiggly line. And we see the difference between 1 neighbor, 3 neighbors, and 9 neighbors. Take a second, pause the video, just briefly notice what about the boundary is changing and why you think it's changing. Okay, so third block observed that as the number of neighbors increases, the boundary is kind of smoothing itself out or getting kind of less complex. And an observation Y is because if k equals 1, then that means the boundary is being strongly influenced by individual examples from our training set. And if those examples are noise, or if those examples are outliers, the boundary is still paying attention to them as if they're important. So if you're if you're basing your predictions on more and more neighbors, individual points are going to have less and less of an impact on the overall predictions and therefore the overall boundary. Okay, so you're just about to predict what you think the boundary looks like for our original data. Notice that for decision boundary, I didn't say that you're drawing a line. The decision boundary is made if you imagine having your machine learning model make a prediction for every single pixel in this entire image, or every single possible example in the entire space of possibilities. And the boundary naturally occurs due to that. So don't think about where's the boundary necessarily. Think more systematically about what would happen if I had my model predict a whole bunch of different points. Would they get shaded as triangles or would they get shaded as circles? And then the boundary should naturally emerge out of that. So give it a try. Imagine k equals 1 versus k equals 3. Where do you think the boundary is going to naturally emerge for each of these? You should actually try and sketch this on your piece of paper before we reveal the solution in the next video. Okay, so these are my sketches. They're not perfect, but they're trying to convey an idea. So it was surprising to a lot of people in third block that there's this kind of circle around here. But hopefully it shouldn't be surprising after you hear what I have to say about it. When k equals 1, of course, any point in space that's closest to this circle should get shaded as a circle. So you would expect to have a little region closest to here that would get categorized as circles. I tried to make my boundary be exactly halfway between the circle and the star in any direction where there's a star. Because if I have, like, let's imagine over here, if I had a point that I was categorizing here, it's closest to that star, so it should be outside that little circle region. If it were here, it's actually closest to the circle, so it would get categorized as a circle. And then over here, clearly, everything within this boundary is closest to circles, and then everything, well, the intention is everything over here is going to be closest to stars. Whereas k equals 3, you see it's kind of smoothed out. There is no longer this region where we're going to categorize anything in here as circles, because when k equals 3, any point in this whole region is going to have majority vote stars. And so there's no more circle region there. Okay, again, third block felt like this decision boundary probably more accurately reflects the pattern in the underlying data that we're hoping to be able to replicate in our own predictions. So they thought k equals 1, probably wrong. So now let's look at an example that's going to make it a little bit more obvious why larger k isn't always better. So it's a little hard to tell what's happening here. You've got some orange circles and some blue circles. This dashed line is a human who drew what they think is like probably the actual ideal boundary. And if you look at the data itself, the data seems to have this sort of like swooping shape for the orange and this kind of swooping shape for the blue. And the dashed boundary is trying to capture more or less what that swoop looks like. So the solid boundaries here are the actual decision boundaries for k equals 1 and k equals 100. For k equals 1, we see that it's probably being influenced too much by individuals. So this blue is probably an outlier, and we would be wrong to predict very closely related examples to be blue. They're actually probably going to be orange. K equals 100, however, the boundary has straightened itself out too much. So a point in the space over here is more likely to be blue than it is to be orange. But it's in the orange group, according to this solid boundary, because if we're looking at the 100 closest neighbors to make our choice, there's just a lot more orange over here than blue. So this one is failing to capture the pattern that's actually there. So the best boundary is probably going to be somewhere between k equals 1 and k equals 100. So these two pictures illustrate the two most important ways that your machine learning models can go wrong. One is overfitting and one is underfitting. Neural networks especially are very, very prone to overfitting, at least the way that most people end up training them. Overfitting happens when your model is overly influenced by noise or outliers. And that's likely to happen if you have a machine learning model that's able to produce a very complex, very nuanced boundary, but you train it on not enough data. That's the situation where you're going to get overfitting. Underfitting is when your decision boundary is going to be too simple or too inflexible to capture the pattern that's actually there. And hopefully both of these pictures illustrate that that's true. So we're practically at the end here. If you haven't tried to do this already, nice things to try with your interactive classifier are testing if the size and location of your image matters. And this is the main reason why your classifiers worked so well on our test data. It's because the test data looks very similar to the training data. But if you were going to start drawing digits in the upper right-hand corner in your interactive classifier, you'd see that your classifier starts to fail because it was never given training images that look like that. So a really common solution is called data augmentation, which just means giving it a greater variety of more representative data. Data augmentation could be a pain if you were going to do it by hand, but a common thing to do would be to write a script. We already have thousands of training examples of handwritten digits with correct answers. Imagine that you wrote a script which takes each example from your current training set and produces 10 images out of it, where you take the digit and then you shrink it and then you put it at random places in the original size of your input. So in that case, you would have taken this image and produced ones that were sort of like this one or this one. And you wouldn't have had to do really any work other than programming. So writing scripts to do data augmentation is sort of a very common thing, very hip thing to do. Let's skip that example. So hopefully you have now more vocabulary and tools for thinking about why, when k equals 1, your classifier worked so well. I was going to have you write about this, but instead, here are a couple things you could work on. This is the second handout. A couple of tips for speeding up what you already have for k equals 1. Some advice for how to generalize it for the k nearest neighbors. And there's also data available there that's not just images. There's spam data and there's also heart disease data. And so if you really want to see what's possible, you can modify your classifier to load those other data files and use a k nearest neighbor to predict risk of heart disease, for example. And I think that would go a long way in sort of helping you generalize your understanding of when and how is this algorithm potentially useful. Good luck. I will see you again on Monday. Remember that our final exam is next Tuesday and Wednesday.